Thank you, Dr. Horst, for setting the stage for what promises to be an exceptional 3 days of discussion. We now move to our first keynote address of the symposium. Professor Bjorn Stevens, Director of the Max Planck Institute for Meteorology, and is one of the world's leading authorities on cloud-climate interactions and their role in the Earth's energy balance. His research has identified different ways in which clouds organize themselves. That's actual clouds, not cloud computing, just in case any of you were wondering. Professor Stevens looks at how varied processes such as precipitation, air-sea interaction, and radiative cooling influence this organization, and how clouds couple to larger scale circulation systems to help determine the pattern of climate change. In his keynote today, 3+1 Problems of Climate Science, he will teach us more about how next generation computational models are transforming our ability to understand climate dynamics, including AI-driven systems. Please welcome with me Professor Bjorn Stevens to the stage.
Thanks very much. Is the sound okay? Is it too loud? It's okay. I think I can click here. I wanted to go here. So while that's playing, I just wanted to thank the organizers and Horst Simon for the opportunity to be here. It's a real pleasure. It's an amazing venue. I visited Abu Dhabi for the first time last year for the IREF conference, and it's a really fascinating place to be. So you might have, if you look here, we practiced this before. There's the end. So that should play. Now it plays. That's the chaos of weather. What you're seeing there is 3 months, June, July, and August, playing out and visualized by fields of precipitation. And in the background, what you'll see is the accumulation of that precipitation. And you see how the chaos of weather structures the attractor of climate. So you see the statistics emerge from the development of small-scale weather systems. You see large-scale waves of, extratropical storms in the northern and some of the southern hemisphere going from left to right. And in the tropics, you'll see small-scale patterns of precipitation going from right to left. You can look at the monsoon developing over India and the Bay of Bengal. And what you see if you did this from year to year is the weather would always look different, but it would trace out more or less the same attractor or the same climate. So keep this in mind. It's how weather makes climate. And the climate, of course, is what we plan around and would like to know when we look into the future. So what I'd like to do in this talk is introduce you to 3+1 problems of climate science, keeping that introductory slide in mind. And I'm going to spend a fair amount of time on just a few graphs and then flip through some things to keep you entertained. But this is one of the graphs, and what it shows is the predictability problem of climate. It's kind of complicated, so let's just concentrate and step through it. In the y-axis, you have scale. It goes from very large-scale global to small-scale local. And on the x-axis, you have time, and it goes from short times of minutes to days to weeks to centuries from left to right. And bounded, the colors are bounded by what we think are predictability horizons, where, on what time and space scales we can predict things. So if you look on the left-hand side of the diagram where it's colored brown, we think of predicting weather. And you see that vertical line, or not the vertical line, the solid line that goes diagonally downwards is sort of the predictability boundary. It shows that as we move to longer time scales, we're increasingly unable to predict shorter or smaller spatial scales. And we understand that why that is. That's just the chaos of weather, and the weather gains its predictability from the initial conditions. So if we know the state of the weather today around the world, kind of like a ball that we set off rolling down the hill, we can figure out where it's going to go for a short period of time. So the deterministic weather prediction gets its predictability from how well we understand the state of the system at time equals 0, and the property of the system as a whole, which tells you how quickly the states will diverge as you move forward in time. And that defines the predictability boundary, the diagonal solid line. The dashed line kind of says how close we are to that in practice. How much predictability can we recover out of the system? So that's all fine, that's all known. But when you go to the blue side, we talk more about the statistics of rolling many balls down the hill and where they will go. We talk about the accumulation of weather into climate. And there we have only a vague idea of what's predictable. We think on the very bottom right, that's the global scale over very long time periods. We can say things about the mean and the variance maybe from not the initial conditions, but from the boundary conditions. What the sun is, how much CO2 is in the atmosphere, the distribution of continents, things like that. So we think the boundary condition, that's why we color it blue, determines the predictability on the right-hand side. But I say we think because we don't really have a theory, so there's no solid line on the right-hand side, and there's different hypotheses about how much predictability is in the system. So if we want to know if the Earth's going to get warmer when we put more CO2 in, we're really talking about the global temperature on long time scales. But if we want to decide how to plan our cities and how to manage our infrastructure, we care more about time scales which are decades and spatial scales which are tens, hundreds of kilometers. And there we have really no idea if the system is predictable. We have no theory. And you can think of that mathematically, this idea of structural stability, that if you have a mathematical system and you change it just a little tiny bit, do the properties of that system change a lot or a little? And in a structurally unstable system means that if you change forest planning in London, it will change the statistics of storms that you have in Abu Dhabi. That would be a structurally unstable system. A small change leads to a big effect. And for the climate system, there's been some speculation that it's structurally unstable, which means that we would just have no predictability where that one is. But the point is we don't know. When we model climate, instead we do things like this. These are not like the first picture. They're schematic diagrams where we talk about EBM, it stands energy balance model. So we say, can we predict the climate without knowing anything about the weather? So all of climate modeling has grown up around this idea that we can describe the attractor, the statistics of the system, without following the ball around the attractor. So we think that there's a large-scale constraint that tells us what the global weather will be. And because of that, we can make simple schematic models like this, where we look at the energy in and we look at the energy out, and we say, well, that tells us the global picture. We play the same game with a more complicated model, which has some regional disaggregation. Maybe we allow an ocean circulation, and we pretend that might tell us about the local picture. Or this would be a traditional climate model on the far right. We try to represent the large-scale stirring of the flow that's associated with these mid-latitude storms, so we have some atmospheric circulation. And we, again, aren't really simulating the weather. We're trying to simulate the climate without the weather. And the question is, does that work? This is what a traditional climate model would look like. It's a lower resolution one. Black versus white is dry versus moist. Colors is rain. It's a bit like that first picture, but this would be a typical climate model that informs global policy. It doesn't leave you overwhelmed in this image, but you see some elements of what the climate system does. You see the westward migration, the west to east migration of the storms in the high latitudes, and the more bubbling nature of the rainfall in the tropics. But you see also there's very little regional specificity that we saw the last time, which comes back to this question of what we'd like to know about climate really is what it's going to mean for us and for what we do. And models like this weren't designed for that. They were designed to help us understand the global picture, how the temperature will change with a given amount of CO2, or if the sun got brighter, or something like that. You could say, well enough, a model like that, it gives us the global picture, and we can make graphs like this. And this is a graph that drives a lot of global politics, and it shows on the x-axis, it shows just a correlation, and it shows a correlation that's been made from models. And on the x-axis, it shows that the cumulative CO2 emissions since 1850, and the y-axis shows the temperature. And what you find when you run models like the last one is that, sure enough, temperature rises as you increase CO2. We don't think that's right because the models do it. We understand it from very basic physical principles very well. I could calculate that curve with a pencil and paper and a few hours of your time. But the models do it as well. They don't do anything different. And they show this linear relationship. And then you can play the game. You can say, well, we don't want the Earth to get too warm. You can decide why, but you said, well, we don't want the Earth to get warmer than a certain temperature, say 2 degrees. And then you could say, well, if we want to keep the global temperature below 2 degrees, how much carbon can we emit if we follow that curve? And if you look here, where we're at now, we're at about 2,400 gigatons of CO2, or 2.4 trillion tons of CO2. And you could say if we want to stay below 2 degrees, by that graph, we should get to maybe 3,600. So we have about another half a human civilization of emissions left in the game if we want. But if you look, on one hand, you see a nice line, but if you look again, there's quite a bit of spread. If we want that 2-degree target, you could say, well, the middle's at 36, but we might be unlucky and we might only have, 600 gigatons left. Or we might be pretty lucky and we might get to 48, so we'd have 1,800 gigatons left. Practically a whole another civilization of carbon emissions. So if we're going to try to do planning, that's a huge amount of spread in terms of how much carbon we can put in the atmosphere to stay below a given temperature. Let alone the question is that we don't really know what 2 degrees means. I mean, what does 2 degrees of global warming mean? How is it different for the decisions that people in this room will make? So it's sort of informative. And I should just say that the spread there comes mostly because of how the clouds behave in the climate system. As the climate warms, if clouds go away, the planet becomes darker and absorb more sunlight. If clouds increase, then the planet will become brighter and reflect more sunlight. So the response of clouds is the big driver of spread right there. When we come to the question of what 2 degrees means, we have another problem. And this is shown here. And it highlights different regions in the world where we're observing changes, right? Last year, I think the world was, for the first time, 1.5 degrees warmer than it was in the pre-industrial time. So global warming is here, and it's not something we talk about for the future. It's something now that we measure and we see things happen regionally which are unexpected. And some of these things are really outside of the sample of thousands of models that we've created before. And this figure shows all over the world. We see changes in circulation over the North Atlantic. We see changes in heat waves over Europe. We see cooling in the Southern Ocean. We see the storms of the Southern Ocean are stronger than expected. There's many, many things that we're seeing that we can't explain. But remember, we want to set a global temperature. And at 1.5 degrees, if we can't really say what that means locally, then it really impairs our ability to say what's a reasonable bound on that temperature. If things can happen locally, could they be dramatic? As some of the more alarmist literature would talk about sudden abrupt changes that are irreversible. Can they happen? And that really depends on our ability to calculate what the future would look like on scales like that, which the models we have until now couldn't do. They weren't designed to do. So that's the 3 problems of climate science. Here is one is just to understand even a way to think about what is predictable. We lack that, or a way to compute in a funny way what is predictable. We'd like to understand how clouds respond to warming if the system is predictable, because then we could say how much CO2 relates to how much warming. Don't get me wrong. None of this is slide rule science that's really precise. It's even just to get a better feel, not a factor of 2 or 3 difference, but a 20 or 30% difference. So how much will it warm for a given amount of CO2? And if we know how much it will warm, how will that constrain what becomes possible region by region? The example I like to give for here is just imagine for a second if a tropical cyclone rounded the Cape of Hormuz. It would just whip all of the warm moisture around the peninsula, and it would rain over, I mean, it's just mind-boggling what that would do. Is it possible? Is it more possible in a warmer world? Fortunately, we have new tools to look at the Earth. Now, this isn't one of them. This is actually a really old tool. It's a handheld camera that was used by the astronauts on Apollo 17, and it's a quite famous picture that people credit with changing how humans think about their world. It's called the Blue Marble. Is anybody here from South Africa? Yeah. You might be too young. Are you over 53? Don't tell me. See, your parents were there somewhere in that picture, thinking about it 53 years ago, almost, December 7th, 1972. And that was a photograph. Back in 1972, we didn't really have a meteorological satellite program. We weren't collecting data from satellites. We had a few ground stations, hardly any in the southern hemisphere. We weren't really launching balloons. There isn't a whole lot of data. There's that picture. But if you piece together the little bit of data we have and put it in a physical model, you can get that picture will look like this picture here on the right. That's what physics gets you. You only saw it briefly. You can see it later longer. But the physics allows you to look at things, and if you believe it got that photograph right, then had the astronauts been on the other side, they might have been able to see the rainfall over the Amazon that shows up in this picture. If they could have seen through the clouds, they might have been able to see the sea surface height field, how that varies, and the Agulhas through flow around the Cape. They might have been able to see the salinity of the water, the freshening of the waters in the Bay of Guinea, the temperature of the water, the upwelling around Namibia, the large-scale structure of fine-scale features of the wind, and how that relates to the clouds as they evolve with the system. And you could actually zoom in and go look at is it lemurs that live on Madagascar? I don't know, but you could go zoom in and actually see what's happening locally. The point being is that physics is a powerful way to generalize, and we understand a great deal of the physics for the climate system. We just haven't been able to compute it until now. And so now we can do computations which look at the Earth in terms of building the climate from the weather, rather than trying to create these gestalt constructs that somehow calculate the climate directly without thinking about the weather. This is an example. Before I said the weather, the way the atmosphere works is pretty simple. It's a greenhouse atmosphere. That means it loses energy to space and it loses energy to the surface. If it's losing energy, the atmosphere is cooling, cooling, cooling. The surface is warming because it gets energy from the sun, and to balance that equation, the surface has to transport energy to the atmosphere. And it does it like this. This is a cross-section using a model like I showed from North Germany on the right and South Germany on the left. And these are convective clouds. They evaporate moisture at the surface. They rise up, expand, condense, rain falls down. The condensation is heating. The evaporation is cooling. That's how the system works. It's like a boiling pot of water. And this is the weather. This is the weather we saw on the first diagram, and this is what it means to compute the weather to understand the climate. And that's what we can do now. And if you contrast that, this is what we did before. So the top picture is computing the weather to figure out the climate. The bottom picture is computing the climate and sort of inferring the weather. And there you see what we do is we kind of statistically paste on what we think is happening in a given situation. But it's unsatisfactory, and it leads to a great deal of discrepancy between what we observe and what we think would happen using the models on the bottom. And the hope is that by using tools like the one on the top, we can do better. This is the other graph I want to spend some time on. There's a lot of information there, but it's a computing graph. It's a scaling graph. It's based on something that I worked on with Thorsten Höfler a couple years ago. And what it shows is, on the y-axis, tau is non-dimensional throughput. It tells you how fast you can compute something. So the question is, if we want to use this new capability that I showed before, what is really computable? And so this time, tau equals 10,000, 10 to the 4. That means that you can compute 10,000 days in one day, which is about 30 years. So every day you could compute about 30 years. So if you look at that red dot up there, 26 simulated years per day, that means you can get about 800 years of simulation in a month. And you could look at 800 years of how the climate system evolves, or 800 times 1 year. That's shown on the left. That's sort of a traditional type climate model run at reasonably high resolution. On the bottom is the scale. That's why it's a coarse resolution model, so 100 kilometers, 10, and 1 kilometer. And you see the points are actual computations we've done on different machines. So if you look at the left, you'll also see the points kind of group around. There's a dashed line that goes down. That's the strong scaling limit. And it illustrates a unfortunate problem of climate computations, which is as you reduce the scale, you have to take more time steps because the time step becomes smaller. And so the strong scaling means that as you go to finer scales, you're taking more steps to get to the same solution, so it takes you longer. So the throughput goes down with a slope of -1. On the other hand, as you go to finer scale, you use more and more of the machine because it's a three-dimensional calculation, so you need, for each grid point, you need 3 times n to the 3 more machines. So that line, the solid line, shows you how much you could fit on the machine. And that goes down as -3 because as you double the grid scale, you have to do that in 3 dimensions. And so what you see on pretty standard computers, this is our 15 petaflop sort of machine, Levanta. We can calculate traditional models, and we can't really fill the whole machine. We have a lot of machine left over past strong scaling between the dash and the solid line, where we can run many realizations and many ensembles. And as we go to higher resolution, we run out of machine. Now, there's new machines. This is Jupiter, the largest supercomputer in Europe, and hopefully will be announced as Europe's first exascale computer. And we've been calculating there. And the pictures I was showing you are the dots on the far right. And what we show here is that we can get nearly half a day per day running across all of Jupiter. So this model uses the GPUs, the GH200 superchips. We scale on just about 5,120 nodes, times 4 for the number of superchips. We use the GPUs fully, we use the CPUs fully, we benefit from new technologies like DACE to parallelize the simulation. And it shows you we can compute on these machines at half a year per day. So if you want to look at a model like the one I just showed you and had a machine like that, you could wait 2 months and you could look at the next 30 years. Or you could back off a little bit and simulate at 2.5 kilometers. It's also not so bad. And you have a ton of machine left to explore different scenarios. So you can compute things that you couldn't compute before on these new types of machines. And I think we're the first application ever to scale across all of Jupiter and really fully use the heterogeneity of the architecture of that machine to kind of mimic the heterogeneity that we see in the climate system and exploit that power of computing. So here I just want to impress upon you the things that we can compute now. And this makes a big difference because it helps us solve these 3 problems. And here on the bottom, if I can just have your attention, it's hard, 15 minutes of attention. What you see is a bunch of lines, and as the lines get more blue, they kind of group together. So on the left, we're looking at latitude, and we're looking at measures of the circulation, like where it rains in the tropics or the extratropics or the strength of the climate circulation. On the right, we're looking at vertical profiles of things like temperature and humidity, clouds. The point you should make is that the lines get closer together. And what we're able to show with these models is that as we approach this 1 kilometer limit, we're converging to a similar answer. So we're really, for the first time, seeing what the equations are telling us about the behavior of the climate system. And if I do this with our model, and I took exactly the same equations and discretized them using someone else's method, I'd have numerical errors on the grid scale. So you'd say on the grid scale, this solution would be rough. And that's a little bit like the structural stability problem. So I would say this is what my implementation wants to look like, the dark blue line. And if I go to my Japanese colleagues who are developing a similar model, they could make their lines more red. And in the end, we could say if we solve the exact same equations, but with different discretization errors, it's kind of the difference between putting a nice new park in London or changing a shipping lane here or there. Different discretization errors, do we come to the same answer? And that can help us address this question of structural stability. It'll give us insight for the very first time. If we converge with one model, will we converge to the same answer with another model? And if not, the implication would be that would be a measure of the structural sensitivity of the system. That's the first question. Given a model, as we converge, we can have a hope of actually really seeing from the physics how the clouds are changing. So we can solve the cloud problem. I think it needs a model at about 100 meters, and I think we'll get there by the end of the decade. And then we can ask really, what does a given amount of warming mean for how clouds change, for how weather changes? You know, how possible is a very different future? And that brings me to the one other question that these models can solve. So this is a Salvador Dali painting. It's his sister looking out a window, and it was manipulated by me to deal with the real question, which is how could our world look like in the future? How can we give people the capacity, if we as scientists understand something about how the world might change in the future, how can we give people the capacity to imagine it for themselves, however they might like to imagine it? You know, it could be somebody working in finance trying to figure out what this tropical storm going around the Strait of Hormuz would do to Dubai. It could be somebody's just imagining what their landscape would look like in a 2-degree warmer world. So simulating at a human scale also creates the databases for allowing people to understand their world and the implications of a world in very different ways and make their own decisions about whether they want that or not. The problem, of course, let me go back before I show that. The problem with this, of course, is it's hard to do. I mean, the amount of data is fantastic. We're talking exabyte of data, the sort of bandwidth we need to do, the visualization. We can't do that for everyone. You know, you dial up and say, visualize that simulation for me. It's just nuts. But we know how to do it. So we can do it in instances. And that is where we come to what you saw before, the beauty of AI. In my mind, AI is such a fantastic tool because it is anything better than coffee? Maybe AI. And AI is good for what coffee is good for, in my mind. It allows us to do stupid things faster with more energy. And we shouldn't underestimate how useful that is. You know, every time we meet and we discuss AI, people really obsess about all the things that it might be able to do that it can't do now. And they forget about all the things that it can do now, which is super useful. And using AI representations of the data, NVIDIA's developed this tool C-Bottle, which is just that. It uses generative AI to try to create visualizations of the future which are consistent with the underlying data that it's trained on. And if you do that, we have a very powerful way to make huge amounts of data interactive for people. And I think that's a frontier, and if we can do that, you can also think through the opportunities in doing that. If you give people simple ways to interact with information of the magnitude that I was showing, then you really have tools that kind of make us ready to deal with an unknown future. And this is some of the idea of what we call EVE, Earth Virtualization Engines, is we don't think of AI as a replacement. It's really the coffee. It's to allow us to do the things we know how to do faster, and that is a qualitative change because it enables interactivity. So we take the world of data and simulation, we use AI to make all of that apparent and usable for people in terms that they find satisfactory. And with that, I would just end and say there's 3+1 problems of climate science. Maybe the first 3 are all one, is what is predictable? If the system is predictable, how much will it warm for a given amount of CO2, the cloud problem? And given how much it warms, what does that really mean on a practical level for how our planet is structured and how our investments are distributed? And the +1, of course, is if we can do that, can we also take what we learn and make it useful for people? So with that, I'll thank you and take a few questions.
Thank you, Professor Stevens, for this presentation. As a data scientist myself, I'm impressed with the visualization and knowledge shared in this presentation. We'll take the floor now for 1 or 2 questions from the audience.
There's one over here. Yeah.
Good morning, Professor. I really enjoyed it, even though I was trying to force myself to follow you step by step, but I think I sort of succeeded. My name is Nicholas Gilani. We are an ag tech firm. Question, you mentioned AI, and it sort of acts like a coffee. Have you when you mention AI, does it include quantum computing, or is that a totally different discipline that may be of use? Because I think it would be, but I'd like to hear your thoughts on this. Thank you.
Yeah, a lot of people are excited about quantum computing, and I hope they're right, because it would really change our ability to compute some of the things I was talking about, and maybe we could compute, though, you know, that curve would look very different. Then maybe even the role for AI is somewhat less. But I'm always nervous about things which are 10 or 15 years away, you know, and always, I mean, you're similar to my age, and you kind of know how nuclear energy is always sort of 10 years away, and has been 10 years away for the last 30 or 40 years. So we will see, but in things where a lot of money is involved, then forecasts can be a bit misleading, and so I'm a bit hesitant to, yeah. Right now I don't see how quantum computing is going to help us on this problem, and so I think using traditional computing with AI is the way to go forward, and maybe I'll be positively surprised about the quantum computing.
We'll take one more question.
In the back, there's one there with them.
Yeah, thank you very much for your presentation. It was really, really interesting. I'm just trying to understand what is your conclusion. Do you think that we can forecast the weather, or is it something that is out of scope even for AI and with a lot of data?
Yeah, so this predictability boundary that I showed you is fundamental. It's just a property of how the system works. And we know that we won't be able to predict a thunderstorm on a particular day beyond a few weeks, no matter how brilliant we are, because it's just an inherent part of the system. Is if you take two initial states which are arbitrarily close together, they will diverge exponentially on a given time scale. And so after a certain amount of time, you just won't be able to know what will happen to a particular storm. However, you will be able to know, and that's where we described, like, imagine a ball rolling down the hill. I could say, well, if I roll a ball down the hill twice, the first time it goes a bit left, the second time it goes right, and I try to make it exactly the same, but it's never exactly the same. When it comes to the bottom of the hill, it ends up in a different place. But what I would notice that all the times I roll the ball down the hill, they describe an envelope that the ball mostly travels through a certain area, and I can say it's on average going to follow this path. And so we could say on average, say in Abu Dhabi, you'll have rainstorms like you had in April 2 years ago, or 2024, a year ago in April. You'll have rainstorms like that on average every 30 years. Those are the sort of predictions we want to make on the climate side. So in the first diagram, there was the yellow side on the left, saying what happens with an individual event, and on the right side of the diagram, where we go to longer time scales and larger spatial scales, we're talking about the statistics of events. But of course, that's what you want to know when you make decisions about infrastructure and investment and financing, is you kind of want to know the envelope. You don't really care if it happens on a Thursday or a Friday. You just want to know if that tropical storm is going to cross the strait. So,
thank you once again, Professor Stevens, for setting a powerful tone for the symposium.